His wealth of knowledge and hands-on experience, Mr. Yadav, a highly sought-after speaker and consultant in the fields of data engineering and automation. His insights into leveraging technology to streamline processes and enhance productivity are invaluable to organizations seeking to navigate the complexities of digital transformation. Sir, please.
Thank you, Millie. So, welcome everyone. Good evening in today's lecture. So, before starting to neural network,
Good evening, sir.
Just a recap of yesterday's session. I told you, neural network was a game changer in terms of laying the foundation for GenAI. So, if you look into the GenAI models that are available, if you want to use it and develop it for further use, it was exposed through OpenAI, Google, and Microsoft and AWS. So those are publicly available, but you have to connect with them basically. If you have integrated ChatGPT somewhere in your application development, so you have to use the API for ChatGPT. Then ChatGPT exposes a small, large, and medium model. So based on various data sets, those models are trained. They have categorized those as small, medium, and large. So before ChatGPT and before all these GenAI that is publicly available over internet, we had the models that we can develop on our local data. Yesterday I mentioned these models are trained on whole world data, and we don't want our model to gain information on what is happening in agriculture in US because we are only interested in India. Or let's suppose I want to translate Tamil into Hindi or Telugu into Hindi. So I don't want my model to learn how to translate French into English or those things. Right? So we want our domain specific problem, like we want the model to be trained on our problem, on our data, and solve our country specific or domain specific problem. So before using these models, you can on local machine you can use the models and input the data into the training set into these models and train them and create those models. So before GenAI, those are publicly available. We have simpler models like linear regression, logistic regression, random forest algorithm, and neural network. So you can build a neural network from scratch. Okay, and while building the neural network or using it or adapting it in any application, we want to learn okay, what is the architecture of the neural network and how we can tweak the neural network for our purpose so that it would predict more accurate and predict more efficiently for our problem. So I'm going to share my screen. Yeah. So I'm going to take a session on foundation of neural networks. So I'm going to explain what is the architecture of neural networks and what led us thinking into that direction, like why we are building this kind of model and what are the types of neural networks in there and what are the applications. And if time permits, we will go into the mathematics part of it, but I will not cover the mathematics part of it. I will skip those slides and we'll focus on basically the equation, not on the actual example that I have included in this. So yesterday I have mentioned how we gain the knowledge, like why to build this network. So we got inspired from the human brain, like how the human brain is working, how the neuron cells within the brain are working, and how the information is passed from one neuron to another neuron, and after that the brain is taking decisions generating the output on top of it. So basically, it is inspired from the biological neuron. Neuron is the brain cell that is there in our brain, and like if you see the structure of the neuron, it takes the input from the dendrite part of it, and it processes the input and then processes the input through axon, and then output is generated, which is transferred to another neuron. Sometimes like it is transferred to another neuron, sometimes the output is enough to take decisions, like to take the final decision. Like if you are recognizing a picture of a cat, then that information is passed to neurons and the output is generated like this is a picture of a cat. So axon is basically amplifying basically the data or inhibiting basically. Either it is filtering or purifying the data that is flowing to take decision, and either it is creating the final output on which we can take the decision. So these two things are happening in human brain, and we through neural network we are trying to mimic the same. So the bottom picture you can say like the inputs are given in the neural network, and then we are generating the output, and based on the various inputs, as you can see in the neuron cell, like those are received through dendrite, we have various inputs that were imposed with weight, and then activation function is there. So I'm going into the detail, but bear with me. I will go into the each and every step of this neural network. So on the basis of this, like we are trying to mimic a particular brain cell into a neural network. So whatever like the neuron is doing, we are trying to do the same thing when implementing this artificial neuron. And neural network is basically a group of neurons, like a group of these artificial neurons, and we have many layers basically through which the data is passed to generate the actual prediction, or to generate a prediction that is very close to the prediction, to the actual value. So that's where from where we got the inspiration. Like why not we build something like brain, and it will take the input and create the output like the brain cell, and we can create a machine which would work in the same manner. So that from there we coined the term perceptron. So it is a neuron only. Like in brain, it is a neuron which consists of dendrite, axon, and output. Here in artificial neural, we call it perceptron, which is also taking input, then combining the input with some weight, and then generating the output in there. So that whole unit is called the perceptron. And how how we are doing the decision thing, why we are doing the weight thing, why we are doing this calculation. So whenever, like if you think about it, when a neuron receives the cell, receives the information, it also transforms the information. It will not feed, accept the information as it is. So whether it is a text image, like whether it is a paragraph explaining a painting, or when you look in the painting and the painting, you understand the same thing. When you read the paragraph, you understand the same thing. So it's our brain that is converting that image and text data into the same kind of information that is understood to us, right? So that's the final output. Like if someone asks about the painting, you will explain the same thing. And if someone asks about the text, like which is describing the painting, you will explain the same thing, and you will get the output from it. So in a similar manner, when the inputs are given, to the perceptron or received in the perceptron, those were imposed with some weight, and bias is also added. Bias term you can see here. B is the bias term, and then it is converted to something else. Like the cumulative input would be the product of input into weight plus the bias. So that is happening within the perception. So here X, like X1, X2, and X3 are representing the input, and WI is W1, W2, W3 are representing the weight, and B is representing the bias. So how X1, X2, X3 are represented? So let's suppose like I want to predict the average height of the Indian by, and I have training data like at 30 years of age and living in Delhi, then and adding more information like living in Delhi and a person has this age. So the Delhi information and the age information is like the age information is X1 and the Delhi information is X. So like it is not exactly fed as Delhi, but yeah, we will convert the textual information into numeric and then we will feed it into perception. So the basic idea is like neural network always receive input in numeric form only. Like no text can go directly into neural net. So so even if you have a picture, text input or speech, that is converted into numerical representation. So I will cover that in further presentation, and that same fed into perceptron on neural net. So that is the basic unit of a neural network, the perceptron, and what it is doing basically. It is creating a cumulative input by imposing the weight on the input and then adding a bias to it. So this is a cumulative input that is created in perceptron. So if W is the weight, and if weight matrix can be defined, so we can define it as a K cross 1 matrix, where like W1, 2, Wk are mentioned. The X is the number of inputs, so we can define the K cross 1 matrix for input also from X1 to Xk. So here the number of weights would be exactly equal to the number of features in the input data. So as I said, like the age and Delhi is the feature of the data, right? And output is the height of the person. So here if I am taking two features, so it would be X1 and X2 only, and weight would be W and W2 only. Only two. If it is 10 features, then it would extend to W1 to W10 and X1 to X10. So why I am doing that? Like why I am creating into a matrix, basically. So you can see further, like in the matrix, it is easy to store like n numbers of features in a matrix, and like it would not lose any value. And as I said, the cumulative input is created by imposing the weight into the input. So here we can like transpose the matrix for weight and then multiply it to the input. Then we get the cumulative input, and in the end, we can add the bias in the cumulative input to get the cumulative input in perceptron. So why we are doing that? Because it is easy to store the values in matrix to maintain it over there, and like we have a mathematical function available which can perform the matrix multiplication easily. Otherwise, if you store it in a single variable or single array and then run it through loop and then take the dot product, then it will be like memory and computation intensive task. So this would make the representation easier, and it would also work helping implementing the neural network in any language. So by seeing this, you can also think of that thing like, yeah, by doing this mathematical calculation only, by doing this mathematical representation and implementing the logic in any language or in any where you can write the code for neural network. There is no need to directly use the model that is provided by open source models or provided by language libraries. You can write a function and create those matrices and create your neural network for your problem. from scratch. So yeah, like every machine learning model that can be converted into a function, or you can create your own code and from scratch and develop it. So it is complex, but yeah, if you have time, you can do that. If you understand the mathematics behind. So here we have understood the working of perceptron, and here I have explained like how the artificial neuron looks like. So here like X is replaced by A1, A2, A3, A4 input and the weight, and B is the bias, and then so till now we got to the input part, like how input is multiplied with the weight and bias is added to it. Okay, so what next? What happens next? Like cumulative input is created in the previous slide. Okay, what is next? So we got the 50% part of it. Okay, like cumulative input is created till this arrow, and this cumulative input goes into this triangle, blue triangle. So what happens next? So here, as I said, like these artificial neurons, the neural network is combination of this artificial neuron, and it has one input layer where the data points go, like the features of the data go as input, and one output. And output differs basically in case of regression, it is numerical variable, like just uh, I have given the example like I want to predict the height of person. So that is a numerical variable, that is only one. But if I want to predict the class, like I want to predict like whether like what is the color of flower growing in Himachal or Uttarakhand, and compared to the what is the color of flower growing in Tamil Nadu or Kerala. So the shades will differ. So there are different red, yellow, and this thing. So red will define one class and yellow will define one class. So there are multiple classes. So in terms of classification problem, there are multiple outputs. And in case of regression, it will be single. And I missed one point, like between input and output layer, there are many hidden layers on which activation function is defined, or like different types of activation functions are used to modify the data and pass it to the next layer or to the final stage of. So this is how the neural network looks in real, like when you implement it. Because the input is going as A1, A2 to AN, then output is generated in terms of classification, it is classes, interrogation is a single data point, and between those are the hidden layers between input and output layer. So everyone is with me till here? Okay, thanks. Yeah. So what we have studied so far. So in a neural network, we have an input layer, output layer, hidden layer, the network topology or structure, weights and biases, and activation function. So I have shown you the input layer, output layer, hidden layers, network topology, weights and biases, how, why they are used, and activation function. The activation function I have not gone in detail, so maybe further I will cover that. Yeah. So here I'm covering like what types of input you will provide to neural network. So as I said, basic is like only numerical values will go as input in neural network. Okay. So sometimes, as I said, like I have age of 30 and the location is Delhi. So how Delhi can be converted into a numerical value? So there are various processes where you can convert the categorical data into numerical value. So in like in when you are learning machine learning algorithm, so it is easier to convert. So like Delhi would be converted into column and a flag would be there like one. If there are multiple cities like Delhi, Bangalore, Chennai, Kolkata. So like it would be converted into columns like Delhi, Bangalore, Chennai, Kolkata, and 0 or 1 would come as a flag within flag value in those features. So yeah, that's how you convert the text data, basically categorical data into that. But like if there is a whole paragraph and you want to send it to the neural network, then for whole textual data in NLP, we have one thought encoder vector and one chord encoder vector. So in like in GenAI also, like you are creating vectors or embedding vectors to represent your textual data, and that will go into the GenAI basically. And like the GenAI also converts all the textual image and video data into numeric, and then generates and understands it, and then generate the does it text generation or pictorial generation or generate the answer for it. So whatever procedure that is followed in neural network to convert the text data, image data, and video data, same is with GenAI also. GenAI will always take it as a numerical. It is like for users, it is like it is not exposed like how it is reading the data and how it is predicting. So it is only like it is not exposed to you. So yeah, that is like a structured data. Basically, many features are there. One features are there, and in many features we have textual data, numerical data. So categorical data can be easily converted into that. For text data, we use the one-hot encoder vector, embedding vector, or TF-IDF representation is one. So for different problems, we can convert the text data into numerical representation. Then we have images. So images data is basically based on pixels. So if it is a black and white image, then it has high intensity or high like color is bright, so it has high value, or if the color is dark or dim, so it is low value. But in case of colored images, we convert the each pixel into RGB value, and then RGB values are converted into numerical matrices, and that is then fed into neural network. So like on the GenAI part, you will get the upload link and upload the image, and you want that to some part of the image picture, or you want to convert the image. But here, like that is the in the backend, it is working like that. It is converting the pixels of the image into numerical representation and then processing that. In the speech part also, like the basic input unit of speech is funny. So like the sound waves we have that are converted into numerical input. So like everyone must have known about the Fourier transformation. So we perform that Fourier transformation on the sound waves and create a numerical view of the speech of the audio, and then those are then further basically taken as an input in neural net. Yeah. So now, like we have covered till cumulative input. So now I'm going next step, like how it is working and how uh, how it is taking the activation function, and how activation, like what are the different types of activation we can use uh, in the neural network. So in a neural network model, the parameters are weights and biases. Okay, and the main motive of our training the neural network is that decide the weights and biases of the neural network. Okay, so when you provide the input to the neural network, it would like by default you take any value of the weights and biases and try to generate the output. Okay, when the output is generated while passing the data to the different layers of neuron, after the output is generated, then it will check okay whether the output is close, prediction is close to actual output or not. Then whatever is the difference, then it will try to minimize the difference or gap between the prediction and the actual output, and then we will tweak the weights and biases accordingly so that our prediction would be close to or match with the actual outcome. So similar, like if you have experience on the linear regression or logistic regression, like we try to optimize the loss function or the uh, uh, accuracy of the model by looking at the prediction versus the actual outcome. So similarly, that is happening here also. So how it is done, I will take it further. I'm not going uh, jump into that, but yeah. Now, like we will learn about like what is happening in the artificial neuron. So yeah, this is the here Z is the cumulative input. So here like shown like x1, x2, x3 are the inputs are multiplied with the weight, then they are summed up and then bias is added to them. Okay. So you can view it like a metric form also. Like this is x is a matrix, weight is a matrix, then a transpose of weight are multiplied to x1, x2, x3, and then bias is added in the end. So that is our cumulative input that we have seen before. Okay. So after this cumulative input is created, as I said, this goes into the activation function. And what are the different types of activation functions? So here, like we have sigmoid, 10h, relative linear unit, leakage relative linear unit value. So I don't want to go into detail, yeah, but to view this, like sigmoid will give you values between 0 and 1. It is never negative, and it is centered at 0. Then 10h would be giving values between -1 and 1. So at different times, we need a different activation function. And it's not like in all the layers, you can use a single activation function. In a layer, the activation function is fixed, but in different layers, you can use different activation functions. So that you can control. So in the relative linear unit, there is no negative value. Basically, if some negative values come, then it will become 0, and if some positive value is there, then it will give the positive value as output. And in the leaky area, relative linear unit, we receive the negative value and multiply it with some epsilon value, so that whatever negative values are coming, it will reduce the magnitude of that, and so that it is under control. And if it is positive value, then it will predict as it is. So these are the different types of activation functions. So what we have done, we have calculated the cumulative input. Now the cumulative input is fed into the activation function, and these are the different types of activation functions. So here, like you see, like Z is used. So Z is calculated here like this, and then Z is passed in this function to get the input from each layer. So I have written some description around here for the same function. Yeah. So we have understood one artificial neural perceptron, like how the input is going into it and how it is creating the cumulative term and then applying the activation function on it and then generating the output from one node or one neuron. But neural network is combination of these perceptrons or neurons, and like it is creating a lot of complexity to it. Like for single layer, it is fine, but if we add more layers, then how it is going to work and how it is going to predict. So we will see in further. So as I mentioned, the weights and biases are parameters of the network, and yeah. And the purpose of training this learning algorithm is to obtain the optimum weights and biases from the parameters of the network. So currently we have the input and input data, and we randomly initialize the weights and biases, and then we will try to optimize with each iteration. So it would be like you give the input, then weights and biases are creating the cumulative input, then activation function is applied, uh, then output is generated. Then if output is far from the actual output, then you tweak the weights and biases again, and then again do the process again. So it would be iteration, so that the prediction would will go closer to the actual output. Okay, so I think there is a question like when to use which activation function in real life scenario. So it depends on problem to problem. So let's suppose your uh, uh, yeah. So let's suppose like the example I've taken to predict the height of basically of a person. Okay, and height of a person can never be negative. Okay, so two activation function I see or three activation function will be removed from this, right, which are predicting negative value. So in that case, you don't want your neural network to predict negative values. So you will say, okay, I will not use those activation functions which are predicting negative. So I will not use 10H or leaky relative linear, right? Because those are predicting negative values. I'm okay with zero. I will then modify the zero values, and because zero is more closer to the height prediction than any negative value, right? So it depends on use case to use case, because uh, uh, if I take another example of scientific calculation, so they are like like and negative values are also very important. So there I don't want to lose negative values, and if that is the case, then I will look into 10H and decay relative union to be included as activation. So yeah, there is no rule, but yeah, it depends on use case to use case, what problem you are trying to solve, what lesson you are doing, and then you can use the function record. Okay, we were there. So I've told like parameters are weights and biases, and what are the hyperparameters? So whenever you build neural network, you will got to know like what are the hyperparameters, because that you can decide before starting the training of neural network. Okay. So what are the hyperparameters, like number of layers? Like you will fix, okay, I'm fixing that we will use 10 layers only, or 5 layers only, or 15 layers only. Right? That is in your, okay. Then number of neurons in the output hidden, in the input hidden and output layer. So basically number of neurons are basically the features that are in the input data. So you can control that also. Like if you have 15 features, but you have performed that principal component analysis and saw that only 5 features are useful, or like those 15 features are converted into 10 features to PCA, then you will use those 10 features in this input. So that is in your hand again. Then the learning rate. So learning rate is step size, which is helpful in updating the weights and biases. So we will cover like how we are using learning rate. Basically, that has very uh, 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 that is very much useful in back propagation when I explain the back propagation thing. Then number of epochs. So number of epochs, like how many times you want to do the iteration to get the optimum solution. So wait a minute. Yeah, so I'm back. So yeah, going into the details, like number of layers, number of neurons I have explained. So learning rate and epochs are number of iterations basically. When you reach to the output and output like prediction is not matching with the actual output, then you do the reiteration, right? You update the weights and biases and again predict the output. So uh, that is like second iteration. Then if that prediction is not matching with the actual level, then you will again update the weights and biases and again do the third iteration. So that iteration is called the epoch. Because the training, whenever you are updating the weights and biases, the input data is passed again in the neural network to predict the output. So yeah, before moving forward, like there are assumptions on neural network. So what are those basically? So basically, if you understand the neural network, like all the layers are arranged in a sequential manner. Basically, there is no series of parallel connection like in electricity. So they are like one layer is sequentially arranged after one another. And neurons within the same layer do not interact with each other. So I will show like what I'm trying to say here. Like whenever like we have seen only single neuron, right? When we go into a network, when the second layer is added after that, then each neuron is not interacting with each other. Like, there is no connection between. So I will show you like what I'm trying to say. The input fed into network to the input layer and the output and from the output layer, so that we have seen. The neurons in conjugating layer are densely connected, and all in layer L are connected to all the neurons in L plus one. Yeah. So the second and the fourth point, I will try to explain it through a diagram. Okay. So yeah, every neuron in the neuron network, that we have covered. Yes, and the last one I have already mentioned, and all the neurons in a particular hidden neuron use the same activation function. So in a layer, uh, so if you see the first layer, like for this layer activation function would be same. For this layer activation function would be same. And like among layers, activation function can differ, but within a layer, the activation function would be same. Okay. Then I'm going to say like how what I'm saying that neurons are not interacting with each other. So here we see like A1, A2, AN are at our input and W1, W2, Wn are weight. Then it is creating W11. So here why it is called W11 is like W1 weight output is connecting with the first element of the second layer, the middle layer. So it is called W1. Then it is connecting to the second uh, data weight of the second layer. So it is W21. So like one, like this is one, then one. So that's why W11. Then it is two, it is one, so it is W21. Then it is three, it is one, so it is W31. So you can see like this output generated from this neuron is flowing into all the three neurons of next layer, right? And it is going with like this output would be multiplied with W11, then W21, then W31, and so on. So these so this point, the previous one, neurons in the consecutive layer are densely connected. All the neurons in layer L are connected to all the neurons in layer plus one. So all the neuron in layer L, so this is layer L, is connected to all the neuron in layer plus one. Okay, so this neuron is connected to all the cells, then second neuron is connected to all the cells, and this neuron is connected to all the cells. So this is what I'm trying to say in that point. And like you can see, the green neuron is not interacting with orange neuron, and orange neuron is not interacting with the purple neuron, right? So that's what it is mentioned here. The neurons within the same layer do not interact with each other. Each other. So that's off, and like it is creating a network, so it is densely connected. Like each neuron of layer L is connected with each neuron of L plus. So these were the assumptions basically, and yeah, this is like pretty like if you create a neural network for that you can do that. So now currently we have covered still like single perceptron or like how a single layer thing is going. Now we will go on like how this output is going as an input to next layer. Yeah, and like here like information is flowing from input layer to on output layer, so it is called a feed forward neural network. So like the data is flowing from input layer to output, so it is also called feed forward neural network, and like there is no loop and simple uh, like in this case you can say it has a single iteration, like in a single go it is predicting the output, it is not iterating again or creating a loop after that. So I've included one example, but we don't have time for it. Right. So yeah, this I'm saying like how it's like in two layers architecture, how the data is flown and how the weights are multiplied to input to create the activation function. So I'm skipping the numeric example part of it. I'm going to the algorithm basically. So the feed forward algorithm, uh, as I mentioned, like we initialize the input. So H naught is denoted by input, and then in each layer we calculate. So WL HL minus 1 plus BL is the cumulative input. Okay, that is represented like this, and sigma is the activation function. The whole input is summed and it is passed to some activation function. Then the output is created. Then when the final prediction is happening, so this is happening among the layers. So when the final output is created, it is like the output HL is the output from the previous layer and it is passed to the final activation function to predict the output. So as I said, activation function will differ from layer to layer, and like it is like in the layer you can use different activation function, and in while generating the final output you can generate different activation function. So this is like feed forward, simple. Input is coming and output is getting it. Okay, so now we come to the loss function. Uh, uh, so if you have learned about linear and logistic regression, there is loss function or MSE or RSS, like mean squared error, residual sum of square error. So what we are trying to do there is like when the prediction is generated by the model, then we see like how much prediction is far from the actual output, and that is represented by mean squared sum of errors, like actual uh, output minus predicted output uh, uh, the whole square divided by taking the mean of those squares, and that function is created, and we so like that function is created, and if we want to minimize that function so that this error is less, so we take the differentiation and take the minimum value of that function. And so similarly, like linear regression, or like how do we find the minima and maxima while doing the differentiation, same concept is used here. Like loss function is calculated like how far is the prediction from actual output, and then on the basis of loss function, the loss function is defined by the gap, and we have to minimize that function so that our prediction is as close to actual output. So by optimizing the loss function, we with respect to the parameters in the network. So we optimize the loss function and we update the weights and biases as per the while optimizing the loss function. So how we are doing that? How loss function is playing a key role in deciding what should be the updated weights and biases. So we have input provided the input to the network, neural network, and generated the output. We calculated, okay, this prediction is between the prediction and the actual value, there is a difference. So we defined that using a loss function. This is the difference. Now, how this difference is valuable to us, so that we can update the weights and biases again, and again feed the input data on the updated weights and biases, and see what is the prediction after that. So how loss function is helpful here. So we can check in later. So yeah, I've given you the example like in regression, and we have mean squared error and residual sum of bias. Classification, we have cross entropy and log. As I said, like yeah, so here like we are taking the total loss, is the sum of losses of all the individual data points. So individual data points are basically the rows. I've taken the example of predicting the height, right? Age and city I'm taking as input. So for particular age and city combination, I have one prediction value, right? So if I have 10 data points, so each for 10 data points, we have 10 predictions. And we will check like out of these 10 predictions, what is the actual output and what is the gap between them. So we have 10 losses, right? 10 gaps from prediction versus the actual. So the sum of all the losses will give you the total loss. And when the total loss is minimized, then we will update the W weights and bias. So what we are doing, so here I'm taking the example of gradient descent. So that is one of the techniques to minimize the losses. You must have heard it linear regression also, like by taking the gradient descent of the error term, we can optimize the loss function. So in my point of view, gradient descent is basically that differentiation thing where we can find the minimum value of a particular shift. So here, like it is denoted as W mu is the new weight equal to W old. The W old is the old weight minus alpha multiplied by partial differentiation of loss function with respect to weight. Okay, so it is that. So alpha here, it is the learning rate. So this is the second time I'm using learning rate. I mentioned learning rate here in the hyperparameter. Like what are the hyperparameters of the rate? So third one you can see the learning rate. Here we are using the alpha, that is the learning rate of this. So you can see like learning rate is impacting the new weight that we are going to derive from the old. So as I said, like when you define the weights and biases by default with any random value and you get the actual output, okay, then loss function is a function of that prediction value and the actual output with respect to weight, and then it is multiplied with learning rate and it is subtracted from weight, and then a new weight is generated. Then these new weights are then assigned to this network. Yeah, this network like W1, W2, W3, W11, W21, everything is updated, and then again input is passed to the network to predict the output. So yeah. So similarly, like for biases also, like it would be biases new equal to biases old minus alpha into partial differentiation of loss with respect to the biases, not with. So it would be that for biases. So in a similar manner, biases are also updated. So like gradient descent algorithm present us with the following parameter updation. So it is like weight of layer L for kj. So kj is the connection detail, right? How the neuron of one layer is connected, of layer L is connected to which neuron of L plus 1. Okay, so it would be like W of layer L, KJ hyphen. So this N is representing the learning rate, and then partial differentiation of loss with respect to the weight and K. So K, so you can see like K and R is basis of the weight in the weight matrix, and L is the index of the layer to which it belongs. So that is happening in that qualification. So similarly, like if you convert this kj into real value, so on layer 2, so W11 weight is equal to W11 weight minus uh, learning rate into partial differentiation of loss function with respect to this weight W2. So similarly, like for bias, I have already mentioned like how the bias is will get updated. So now we are at the output, and now we are doing the back propagation. Okay, so I have not explained back propagation. We'll take the time. Okay, so so you see, like now we have generated the output, and on the basis of the prediction that we have generated, we are comparing it with the actual output, and from the gap, from the loss function, we are now updating the network backward. Right? We are at the output stage, and now we are backtracking that. So that is called back propagation. From the loss function, we are again revisiting the net in a backward direction, and then updating the weights and biases of these. So this whole concept is called back propagation. So how the equation for each and every weight in the length would look like, it is defined here. So so here, like the equation for loss is y half of y minus S2 is that. So S2, as I mentioned, is the final output. If you have seen in the example, then how cumulative input is decided. So it is S1. It is the input. It is for a particular layer. So it is like weight into the input plus bias term. And then activation function we are using 10 for this. So it is one example that I am showing, and how it would help in creating. So this is the loss function, and if you can see, you can see like
Sir?
yeah. Hello, yeah, Nitin,
Yeah.
you are saying. You are saying something.
What happened, sir?
You are saying something.
No, sir. No. Please continue.
Okay. So, so the purpose of what is the purpose of doing that? So when I'm taking the partial differentiation of loss function with respect to some weight, so you can see like y minus s2. S2 again can be written as a function of this sum of this cumulative stuff, right? So like when you do the partial differentiation, then s2 can be replaced with this function, and then you can do the partial differentiation easily, so then no terms are zero. Because here you don't see any weight in loss, right? But here, like S2, the prediction thing, can be converted into weight form. So I can show you in further slide. Yeah. So like instead of putting S2 value in this, here we are using the chain rule. Like loss function is done partial differentiation with S2, then S2 is partial differentiated with Z2, and Z2 is partial differentiated to weight. That is basically converting this partial L into W2. Instead of replacing the values, we are doing the partial differentiation. So you can see, like here, loss function can be easily differentiated with S2, uh, then S2 can be easily differentiated with Z, then Z can be easily differentiated with the weight. So that chain rule we are using to derive. So not going into the exact, so here like first term is this, second term is this, third term is this. So we are doing the individual partial differentiation of first, second, and third. So not going into much detail in that, yeah. But want to show like now, like in the previous example, we have generated the output. Now we are back propagating and updating the weights and biases backward. So that's how like back propagation is working. So you can get into the actual mathematics of it, but later on because that would take time. Like 1.5 hour session is not enough to see the exact calculation with this example. So here I'm saying like how like W21 updated is equal to W2 on this. So actual calculation comes like this after we get the new values for the in different layers. Yeah. So the pseudocode for this neural network, like how it is creating or generating the thing. So as I said earlier, also like you can write your own code using this pseudocode and make your own neural network in terms of. So what would be the output of this pseudocode or neural network? So the output would be the weights and biases of the network. So that the values you got in the weights and biases, you can take it on the new data and see like the prediction is working fine on. So yeah, so the training of this neural network, the purpose of training this neural network to decide the weights and biases, the optimum value of those weights and biases. So those are the parameters, and like you can use hyperparameters to optimize the efficiency of or optimize the prediction value of the algorithm of the neural network. Okay. So just going through the pseudocode for this, like first we initialize the output, we decide what are the features we are going to use. Then the forward propagation starts, like we calculate the cumulative input. We then after cumulative input is calculated, we apply the activation function on top of it. Then for each neuron we do, and in a hidden layer or in a layer, the activation is same for all the neurons. Then after getting the activation function output, whether it is for regression or it is for classification, we pass it to another layer. Right? So if it is only one layer, then it will directly generate the output. But if it is another layer in the sequence, then it is passed to another layer. Then another layer does the same thing. It will create the cumulative input. Then activation, if that cumulative input is passed to the activation function, and then it is like output is generated or it is passed to another. So that's forward processing. And also like if the output is generated, then the loss function is created, and from the loss function you can see how much we are deriving from the actual output, and then we will try to optimize the loss. Then the back propagation exists like when the final output is created, we have calculated the loss function. From the loss function, we will try to decrease it. We can use a different loss function, and then by optimizing the loss function, we can update the weights and biases of the network in a backward direction. And like if there are multiple layers, then we have to go one by one and update weights and biases. And after all the weights and biases are updated, again we will input the data with on the new weights and biases of the network. Then we will again do the prediction. So you see, like first we have generated the output, then as per the loss function we trace backward, we have updated the weight and bias, then we have again provided the input in the layer and again generated the output. So you can see number of epochs are coming, number of iterations we are doing. So that are also controlled like through hyperparameter like how many times you want to do this iteration, right? So like that's why like parallel processing is happening and various computation machines are provided so that you can do the epoch correctly. And it is not like let's suppose you have mentioned do it 20 times. Okay, so for each time it will give you the accuracy result, like how much accurate your output is, prediction is, and how much it is deviating. So it will calculate the variance, it will calculate the accuracy, and for each step it will give. So it's not necessary that you will use the model that is generated after 20th step, but you can see, okay, after 15th step it is giving maximum accuracy. So that weight and bias is the optimal solution. So you can use the model weights and biases or the model which is generated after 15th iteration. That is also possible. It is not like whatever number of epochs you will just use the model after that. So that is the flexibility called. You can anytime go back and basically choose whatever model you want to or use. Yeah. So yeah, still there like I was explaining the architecture of neural network, how it is working and what is happening within the network. Like most of the people don't expose it. Like most of the GenAI or uh, language defined functions are not exposing what is happening. So if you understand this, you can build your own neural network. So it is basically uh, metrics of weight and biases, which would fit to your problem, right? And when you are like using the inbuilt functions, also you will get to know like what are the hyperparameters. Okay, so it will ask like there you can mention like what activation function you will use, what loss function you can use in your neural network, what learning rate you can use, what is the number of epochs you can use. So while using that, you will get to know, okay, this learning rate is used in that way, and what is the number of epochs. So it would be helpful when you try to build something for yourself or something for real-time application. So yeah, so the last part of this is like I want to cover like types of neural networks. So basically, I've already covered that. Like feed forward network, I have already explained to you guys what it is, like simple thing, like we saw at the input end. It's passed, the data is passed to the layers and output is generated. So it is mainly used for classification, simple classification and regression tasks. So yeah, like feed forward is used many places, but not only feed forward neural networks are used. Like it is used with combination with other models or other. Like we can combine lots of feed forward neural network to create another neural network. And it's not like if you work in big organization like NASA or ISRO, so these neural networks are used for small tasks. Like it's not like uh, uh, if predict the age of the star directly. So in predicting the age of the star, also like there are various parameters used in that. So let's suppose in my business, we have to predict the delivery time of a particular driver. So delivery time is we are not predicting delivery time directly. So it is dependent on many factors like distance, okay, whether the food is prepared or not, or whether the food is uh, like a driver, like while picking the order, driver is nearby kitchen or not. So it depends on various factors. And for like if you split the bigger metric into smaller metrics, you can build model for smaller metric to basically combine those smaller metrics to create the final. Swiggy and Zomato are already doing that. They are not focused on the delivery time, but they have created delivery time. Like what is the pickup time? At what time uh, driver is picking the food from the restaurant? Then what is the restaurant leaving time of the driver? So there is a time gap. So they have a model to predict that of pickup time to kitchen leaving time. So what is the drive time from kitchen to that delivery location? That thing. Then from that uh, kitchen, like a driver reaching to the society gate, because the entry also took time. So that factor also included in that. Then from society gate to reaching to the flat, that factor is also. So that delivery time is split into various minor factors, and then they have model to predict each of these minor factors, and then provide the final delivery time uh, of food. So that is currently used by giant companies, and they are. So yeah, second one is convolution neural network. So CNNs are basically specialized in grid-like data, and mainly they are used in image classification, object detection, facial recognition, and medical image analysis. So the example for these are AlexNet and VDGNet, ResNet, which are already doing that, which are already doing the facial recognition. Also, like CNNs are used in object detection, like in a automatic car driving, you can see like uh, if a person is on the road or not. So that in there also like CNNs are used. So these are types of neural networks only. Within the neural networks are used, like in convolution you have pooling layer and activation layer and dense layer. So like from the image they can extract information and tell you what objects are present in the image. So yeah, parents are very useful on the image and analysis and image detection. Then yeah, a normal recurrent neural network. So sometimes neural networks are also called recurrent neural networks, because uh, they like those were the basic type of neural networks, and from neural network, recurrent neural network came first, and it started using like, and it is used for processing sequential data, and natural. It is used in time series analysis, speech recognition, and NLP. So that was used, and like as I explained earlier, also like recurrent neural network has the problem of exploding and vanishing gradient. So to overcome that problem, we have introduced create in the RNN. So that shortcoming is overcome in LSTM, long short-term memory, which we're using gates to remove that problem of vanishing and exploding rate. Then like LSTM are like another variant of RNN only, but a better, so, better than RNN. Then again we were using gates. So in LSTM, so why that gated record unit GRUs are one step ahead than LSTM, that they have used the gate of in an optimal manner, and they are like better than LSTM in some cases, not in all cases. Like when LSTM were launched in the market, like everyone have started using it, and like everyone like it was great and nothing is better than that. But yeah, then get it return or unit. Yeah, after that we have uh, the auto encoder, basically encoding of data. So we have talked about it. Like we have encoder specific like models which are only using encoders, and models which are only using decoders. So those are useful in uh, dimensionality reduction, anomaly detection, and noise removal. And the example for them are denoising, autoencoder, and variant autoencoder. GANs we have covered yesterday also, like they have generator and discriminator, and they are useful in image generation and style transfer. Style transfer, I have explained yesterday also, like it is to convert your real-time images into animated form, or in anime. Basically, you want to tweak your images. So the image filters coming on the various mobile cameras or Instagram, so that are using that only. So then the transformer, yeah. So the best RNN so far. So it has encoder and decoder, and it is using self-attention, and all the parallel processing of input will happen. So yeah, so transformer networks are now used in GPT and BERT, and they were trained on a lot of hyperparameters, you can say parameters, and then uh, and lots of data input. So when you see like hyperparameters and parameters, and when you hear something related to GPT or any GenAI, then you click like you will get to know like whatever I have explained today. What are the parameters like weight and bias rate, and what are the hyperparameters. Then you can connect the data. Yeah, so that's all I had to share with you guys today. So anyone has any questions? I think some questions are there. Can you please summarize types of
Hello, Millie.
If anyone have any question, please ask.
So Saranya has asked one question like, can you summarize the types of neural networks? So basically, as the new variants are going to come up in neural networks, so there will be increasing types of neural networks. But whatever the types of neural networks known to us so far, I have explained like RNN, CNN, autoencoders, GANs, and transformers. So these are the basically 5 types of neural networks, on the basis of which various models are created.
Okay. Thank you, sir, for delivering such an enlightening session.
One more question, Millie ma'am,
Yeah,
by the
okay.
Sudhakar sir in the chat box. Just a minute. There are multiple questions here. One question from the Sudhakar Devedi sir. What GPU architecture we require to implement this?
So yeah, for
Ji.
GPU architecture, like basically it is used for video and image analysis only, because the pixel data that is converted into numerical form fits into that GPU architecture. So if you know the working of a GPU, it takes the information in terms of pixels and pixel values, and operate on it. So uh, yeah, like you can use GPU for other things also, but you have to convert data into that grid-like structure that systems have, and then like GPU would be used, and it would perform better in that. But yeah, like it is best used for images and video.
The another question is that how to choose suitable OSS function as we have many types.
Yeah, so as I explained, like there is no fixed choice. Like it depends on problem to problem, right? So as I said, like some functions are giving negative values, but if I'm predicting the age of people, that can't be negative, right? So I will completely discard those values.
Question?
Yes, one question from Abhijit Mishra. How a combination of different neural network can be
Okay,
considered?
thank you, sir, for delivering such an enlightening session. Your expertise made the experience incredibly engaging and insightful, providing us with valuable knowledge and inspiration to explore further. Thank you, sir. Thank you so much.